Hey, everybody. This is Fernanda, Foerrter speaking. You might know me if you've spent any time in the DOE system. I used to work at Oak Ridge National Lab. I worked there from 2012 and 2018. Although now that it's 2024, I find that fewer and fewer people remember me working at the lab. But that's okay. I moved on from the lab and ended up getting sucked into the world of vendors. So now I work for the dark side. I spent some time at NVIDIA, and then after that, I ended up working for a couple of startups. And I ended up with some folks from NVIDIA who ended up calling me to come work at Voltron Data. So let me tell you a little bit why I'm here and what kind of HPC we're doing here. So these are our founders on the slide. Josh Patterson and Rod actually met during a project for Oak Ridge National Lab, where they worked on a application that ended up becoming a finalist for Gordon Bell. And they worked together. Josh was the primary driver and creator of Rapids at NVIDIA. Keith was part of Rapids at NVIDIA. And Rod created an application called Blazing SQL, which was a SQL database on a GPU. During that project with Oak Ridge National Lab, they realized that they had something here that maybe that they should combine forces and actually go forward with it. And if you know anything about the world of data analytics, you know that the applications are, or at least the options for working in analytics, it's either you're working with monolithic databases or you're working with the sorts of things that are like Apache Spark or Hadoop. What we were hoping to do is that we were hoping to put some of that workload on the GPU and take advantage of the bandwidth that comes with the GPU, right? Analytics often depends on bandwidth because you're trying to crunch through a lot of data. And as part of that underlying baseline for working on a GPU, part of what we've done is we've gotten into open data standards, and we've gotten into working with things like Apache Arrow, which is like a columnar data file format, not just a file format, but format, which has all sorts of libraries having to do with communications like Aeroflight and ADBC, which is a database connectivity. So we're trying to get to build a composable data system, a composable world where an engine has been extricated from these monolithic systems, and now we can place this engine near the data and run this engine super, super fast. So we have some of the benchmarks that Trent had shown here. Trent, if you can go back.
Yeah.
We beat Spark quite a bit. So we've succeeded in our mission, which is to build a Spark, an easy Spark replacement for data analytics. And all of the benchmarks that we were able to run, we are the Theseus part, which is the name of our engine, is Theseus, as in the ship of Theseus, that was part Blazing SQL and some of the other work that we've done. So we replaced it little by little and became the ship of Theseus. But we beat Apache Spark by quite a bit, saving folks a lot of money and a lot of nodes. And all of that analytics workload that currently sits on the CPU, we see it all moving to the GPU and to accelerated hardware. So that's what we've been working on. And then at some point, we had one of our customers come in and ask for us to integrate Chapel to Theseus, because we have the capability of putting UDFs within Theseus. So user-defined functions can be shipped, and they need to be compiled into Theseus as backend. And so Trent's going to talk about a little bit of that work, and I hope you have enough time, Trent. Go for it.
Yeah. No, perfect. Thank you. Thank you, Fernanda. So, yeah, I'll talk a little bit about Chapel. So, I mean, at its heart, Theseus, it's a GPU accelerated engine. So its bread and butter is your traditional relational database operations, joins, filtering, aggregations, projections, that sort of thing. We can appreciate for your average HPC case, it isn't as isn't as narrow as that. So, there's a lot more nuanced, diverse computational needs in HPC. So the general approach that we've taken, and it's a common pattern within other database vendors, is to have this support for these user-defined functions. First-class citizens that you can call directly from SQL and are accelerated also on the GPU, and are otherwise indistinguishable from any other operator that you might find within a SQL dialect. So our UDF core framework is in C++, our product's primarily in C++, and it calls various CUDA components. So the general approach to writing these user-defined functions is that you author this C++, in line with our guide. We'll provide the headers and whatnot, and then you're basically integrated into our system as a first-class sort of SQL component. So Theseus and Chapel is kind of interesting. So we had a lot of interest from customers that kind of expressed almost a contractual need to have us support Chapel, and the way to achieve this was via our UDF framework. So we wanted to ensure that if people are coming to us wanting to write Chapel, we don't come back and say, sure, but here's all this C++ you need to write in order to leverage your Chapel. So we wanted to reduce the barrier of entry and try and minimize, if not eliminate, any of the C++ that you would need to write in order to bridge the gap between our engine calling a Chapel engine. So honestly, is phenomenally easy. Thanks to you've got some pretty robust C interop facilities within Chapel, but someone pointed me in the Gitter channel. Someone pointed me at the Chapel Python library that you guys provide. That has phenomenal AST and introspection support. And I think after being pointed at that, it only took me an evening to kind of, and this is by far a testament to the library itself. It only took me an evening to figure out that I could, you could author your UDF in a certain way via Chapel. And then we could write some Python that sucks that UDF in Chapel and then does AST analysis on it, and then converts it into a corresponding little C++ module bridge that allows us to incorporate it into SQL as a first-class citizen. So what's it look like? Well, basically you need to make two decisions. How do you want to, well, one decision of which there are two options. How do you want to return data back to us? So there's this particular pattern that's being depicted here. There's one on the left where we'll pre-allocate the results for you, and then you just write to them. So obviously the array sizes would be equivalent for all of your parameters here, and we can infer from the sizes of A and B that the necessary sizing and types that we need to make the resulting array. Or on the right-hand side, you could, if you need to return something that doesn't fit necessarily as easily into a simple array reference, you could create the array yourself and return it back to us as a Chapel convert to external array. And then essentially that's all there is to it. That will allow you to then, with the supporting C++ scaffolding that you don't really need to deal with, that will allow you to directly call Chapel from a SQL environment and a GPU accelerated SQL environment, and you'd have full access to all of the bells and whistles that you would normally have for Chapel. So there's definitely some work that we could probably do with the Chapel folks to look into potentially refining how arrays are transmitted over the C interop boundary. Internally, we've put a lot of work into the Arrow C device support. So Arrow, it's an open source, very vendor neutral, has the ability to represent device arrays in a very platform agnostic way that allows you to encode within the array itself. Is this on host memory, GPU memory, NPU memory, TPU memory, and encode an actual schema within it as well. So you can say this is an array of DICs of strings that map to ints or things like that. So there's a lot of things that could be done to enhance this down the line. But yeah, that's the essence of Theseus and Chapel. So any questions?
Okay. Do we have any questions for our speakers? Okay. I have one. So I guess to the extent that you can talk about it, I mean, it sounds like your customers were interested in Chapel because of its GPU neutral features. Are there other aspects of Chapel's or features that you think they would be interested in for using in these UDPs?
Yeah, it's somewhat hard to answer. I think the interest in Chapel and the reasons vendors sort of gravitate towards it are strong. There's things that Chapel can do that there's just no real other equivalent that can be done. So as for whether or not we have much visibility into, well, how do you then pair that with a GPU accelerated database? That's not something we have a lot of insight into for numerous sort of contractual reasons, but it's there's definitely some interesting work going on in various areas of the industry.
I was going to say, as you can imagine, a very important customer asked us to do this integration, and we have done what they've asked us to do.
Yeah.
As far as the use case and how deep it goes, we're not really sure.
Sure. Okay. So thank you very much, Fernanda and Trent.